So, when we look here, this is an endothermic reaction, so our delta H is going to be positive. Now, I heard someone say it speeds up a reaction, the EA speeds up a reaction, but it starts, the energy of activation is what we need to start it. What speeds up a reaction? A catalyst. So how does a catalyst speed up the reaction? Well, the temperature is not just heat them up, it is going to speed them up, but that's not a catalyst. The catalyst is an actual substance that we add to the reaction.
It decreases the activation.
Okay, so what did he say over on this other side?
Decreases the activation.
Okay, decreases the activation energy. It provides an alternate pathway. So this is with a catalyst. Speeds up a reaction. Without changing itself. So the catalyst is not consumed in the reaction without changing itself by providing a different pathway with a lower EA. A different pathway with a lower EA. And I use the example of the 49ers heading west on the gold rush, and they came across the Rocky Mountains. So they have this big hill. Now they could have gone straight over Pikes Peak, the highest point in the Rocky Mountains in the continental United States. So they could have had gone straight up and over. They would have gotten from point A to point B, but it would have taken them a long, long time and had to use a lot of energy to get up over the highest point. Or others found a pass, a place to be able to pass between the mountains that the hill wasn't quite as high. And so they still went from the same point A to point B, still got to the same end point, but the pathway was different with a lower hill, so it took less energy and they got there faster. So that's what a catalyst does. It provides a different pathway. Now, when we study kinetics, when we come back somewhere in the end of January, early February, we're going to look at what's called reaction mechanisms, the different steps, the paths, because when a chemical reaction occurs, it's not just A plus B automatically goes to C plus D. A lot of times there's what we call intermediates. There's things that are formed in the middle. There's 2, 3, 4 steps in the path, and we call that the reaction mechanism. A catalyst provides a different mechanism, a different pathway that just has a lower energy of activation. And as a result, at any given temperature, more molecules can make it over the hill. So right now, if I again was to take this PEZ quiz that we're going to take in a second, if I was to take this, right now the paper is hitting this, but there's a certain energy of activation that needs to be overcome and to start the reaction. Now, there are 2 ways in which we can speed up this reaction. We give it more heat. Now, the energy of activation stays the same. We just give it more energy, more oomph to get up and over the hill. That's what lighting the fire does. Giving it more energy, more speed, more molecules have enough potential energy, then they have enough energy when they collide to break bonds and form bonds and to start the reaction. Or, if there's some catalyst that we could add, then it lowers the hill, so at room temperature, we don't have to increase the heat at all. At room temperature, then, more molecules can make it up and over the hill. So you either give them more energy to make it up and over the top, that's heat them up, or you lower the hill, so at that temperature, more molecules can make it over the hill. That's how we speed up reactions, 2 ways, either with heat or with a catalyst. 2 of the 4 ways that we do that. Okay? So we look at this graphically. We can always see then that things want to go to a lower energy. This is going to be the favored reaction. So C, under this, C, nature favors exothermic reactions. Nature favors exothermic reactions, but we just saw an endothermic reaction occur. So that doesn't mean that endothermic reactions can occur. It's just going to be the second driving force is going to be entropy. that's going to drive an endothermic reaction. In terms of energy changes, it always wants to go to a lower potential energy. Lower potential energy always means more stable. Lower potential energy always means a more stable state. Okay? So whenever we're talking about stability, a more stable molecule, it's always going to be the lower. Even when we're talking about electronic transitions, we add heat or electricity, make the electron go to a higher energy level, it just naturally wants to come back down because everything in nature wants to be in that lowest possible energy state. So it comes back down to that ground state. As soon as we turn the lights off, turn the energy off, everything gets back down to that ground state, the lowest possible energy state. Everything in nature tends towards that lowest possible energy. Again, it's potential energy. Not necessarily coldest temperature, the lowest potential energy state. Now, if we want to, how then do we calculate that? This would be E, I guess. Two ways. There are two ways to calculate delta H of the reaction. And we're only going to get to one today, and we're barely going to get to it because we've got to stop here in just a second. Two ways to calculate delta H. The first is delta H of the reaction is equal to the sum, that's the summation sign. I don't make a very good one, but that's your calculus summation, that's your Excel spreadsheet summation sign, okay, your Greek letter sigma. Sum of the delta H of formation of products minus the sum of your heat of formation of reactants. Now this degree symbol right here, this always means standard conditions. Now these standard conditions are different than gas law standard conditions. They're similar but a little bit different. Instead of being 0 degrees, it's going to be 25 degrees Celsius. It will still be 1 atmosphere. And then if it's a solution, it's going to be 1 molar in terms of concentration. That's what standard conditions are. So anytime we look in the back of the book, anything that's going to be standard, if you have a degree symbol right here like this, that means you know the temperature is 25 degrees. You don't have to be told the temperature. By seeing this, you know it's 25 in 1 atmosphere. So you know the temperature and pressure. Now, so what we need to know then is what does this delta H, what is delta H of formation? It is equal to the heat of formation, which is equal to the energy change that occurs when a compound is formed from its elements in their natural states. Okay? Now, examples of this are going to be if we combine hydrogen gas plus oxygen gas, and we're going to say 1/2 because it's always to make 1 mole, making 1 mole of H2O liquid. We say that the delta H of formation, the delta H of this reaction is equal to negative 285.83 kilojoules per mole. Now, so what does that mean? We say that the heat of formation, the delta H of formation for all elements is equal to 0. Elements can't be formed. Elements are already formed. God did that, Mother Nature did it, chance and circumstance did that, however you believe we got here. Okay? Elements are already formed. Okay? Elements are already here. We can't form them. Now, again, we can't know how much energy is in this piece of paper. We can only measure energy changes, so we're just doing everything relative. So what we're saying is, okay, we're just arbitrarily saying elements have a 0 potential energy. So when hydrogen and oxygen combine to make water, how does water's potential energy, how did the energy change? What happened to the energy when hydrogen and oxygen combine? Well, we know that hydrogen is very flammable, right? Okay, we've heard test tubes bark when we put the flame over the hydrogen gas. The Hindenburg exploded because it was full of hydrogen. The Space Shuttle Challenger blew up because the hydrogen fuel tank was leaking on takeoff, and it blew up. And so hydrogen gas is extremely flammable. So when hydrogen and oxygen burn, hydrogen burns in oxygen to make water, negative 285.83. That means 285.83 kilojoules were released to the surroundings. Which means that the water now has lower potential energy than the hydrogen and oxygen did. So we're saying now that the potential energy of water, liquid water, is now negative 285. Just simply means it's less than the elements themselves. So our heat of formation is a negative value. Now, if you combine two things together and it requires energy, it's endothermic, surroundings get cold, well, then it would be a positive heat of solution. So that means then that the products have more energy. They're in a less stable state than the elements were. So we're just saying then that the products, these compounds, we're saying the relative potential energy is based upon how were they formed from their individual elements. So we look at it now. That if we did another example of that, I'm just going to put it right here. Carbon solid plus oxygen gas goes to CO2 gas. The delta H of formation of CO2 is equal to negative 393.5 kilojoules per mole. Now, first off, what do you think the natural state of carbon is? It is a solid, but carbon, remember, has several allotropes, different forms of the same element in the same phase. Diamonds and graphite and coal. What do you think the natural state is? If you write it down, you will know. Graphite. Because it's your pencil, lead. Graphite. If you write it down, you will know. Graphite is the natural state of carbon. Now, that's generally always told to you, but that's just a nice thing to know, that your pencil lead is the natural form of carbon. Otherwise, they couldn't charge so much for diamonds. So what does it mean, negative 393.5 kilojoules per mole? It's exothermic. So that means we're saying that CO2 gas, when we exhale, those molecules have that much relative potential energy. Okay? They're actually even more stable than a water molecule is. So when we go then to calculate our delta H of a reaction, we just can look up the values from the back of the book, and we'll just do one really fast. So if you go to page 1123 in the white book, hold your finger in that page, and then turn to page 209 at the end of chapter 5. So we want one finger on page 209, one finger on page 1123. And on page 209, number 71A says SO2 gas, 2SO2 plus O2 gas makes 2SO3 gas. Okay? So we go to page 1123, Appendix C, and we look up and we say, okay, the delta H of this reaction is going to equal the sum of the heat of formation of products minus the sum of the heat of formation of reactants. So, delta H of the reaction is going to equal, well, what's the heat of formation of my products? On page 1123 or 24, you find sulfur, find SO3 gas. Negative 900 and maybe it's 600. Is it 600? SO3. Look under sulfur. SO3. Really? The other class didn't get that. SO3 gas is negative 393.2. Okay, so we're going to say, now that's per mole, so we're going to say 2 moles times negative 395.3, 2 kilojoules per mole. Okay, that's my whole products minus the sum of 2 times what is SO2 gas? And we're looking at delta H, right? Okay? Negative 296.9 kilojoules per mole. Plus, what's the heat of formation of oxygen? 0. So now we just do the math, which is simply going to be that. So someone just get me a number. $790.4 plus 593.8. Okay, so it's almost 200, not quite 200. Okay, 186.6. Is that right? Negative 186.6? 96. That's what I had. Kilojoules. So, that's how much energy we could expect to be released when sulfur dioxide is burned in the presence of oxygen to make sulfur trioxide.
The negative just means it's exothermic.
The negative simply means it's exothermic, means the energy is being released, it's being given off. Positive means that it's going in. Now, on Monday, we'll go in and look at doing more of these. These are very easy, very straightforward. We'll look at the second way of doing this, which is going to talk about bonds broken and bonds formed. We'll have to be able to draw our Lewis dot structures for that. And then we'll move on. Okay?